All right, folks, it's Bass Action back in action. In this video, we are going to cover two critical topics in pre-calculus, and that is going to be interval notation and finding domain algebraically. I'm doing these two together because finding domain algebraically is a great way to practice our interval notation. So let's start here on the top with our interval notation. So we're going to take a look up here, and a couple things before we get started. First, all intervals will always be written low to high, so the smaller number will always need to be on the left and the larger number will need to be on the right. The other thing is that we're going to have two types of intervals. One is called bounded and one is called unbounded. The only difference between those are bounded intervals have have integer values for their beginning and the end, and an unbounded interval, you can see here from our number lines, are going to go from positive or all the way to positive or negative infinity in one or more of the directions. So that's really that major difference there, and beyond that, that's not too important, that distinction. What we're going to do to understand how to write things in interval notation is we're going to take a look at how we've been writing things in our algebra days, okay? So really since your middle school days and all the way through Algebra 2, we've used this type of inequality notation. Now, from those past math classes, you can recall that an inequality sign that does not have the inclusive symbol, if you translated that to a number line, you would use open circles for those values. If you had the inclusive bar underneath those inequality signs, you would use solid circles there. You would close those circles on that number line. And of course, we can remember that, of course, you could have a mix. You could have an open circle and a closed circle, okay? All we're going to do is we're going to translate these open circles and these closed circles to parentheses and brackets. So beyond that, this really isn't going to change too much for us. If we understand that this inequality notation would translate to this number line notation, then if we want to translate this to an interval notation, what we're going to do is we're going to take the two open circles and those are going to become parentheses. And then we're going to take the numbers on the number line, remember low to high, and we're just going to write -4, and we're going to separate them by a comma, and 3. Now, this looks very much like an ordered pair, and you as a mathematician are just going to need to recognize the context of the problem and recognize that this should be an interval of numbers, all of the values between -4 and 3, and it's not a specific location on the coordinate plane being an ordered pair. For our next one, we're going to take our solid circles, and those are going to translate to square brackets. Now, you do need to be very careful with your handwriting and make sure those look like square brackets and not parentheses. And then just like before, we're going to take our numbers from the number line. We're going to put them inside from low to high, separated by a comma. That's all we got to do. On the next one, we're going to have a mix. The open circle will translate to a parenthesis. The closed circle will translate to a bracket. And again, take the numbers from the number line, low to high, put them inside, separate by a comma. Now, when we get to these unbounded intervals, what we're going to recall is, of course, these notations look familiar. X greater than or equal to 6 would start at 6 and go all the way to positive infinity. What we're going to do to simplify this is we're going to put a little infinity sign there on that arrow. And when we translate this, our solid circle, we know from up above, is going to become a square bracket. But the infinity symbol is always going to be a parenthesis. It will never be a bracket. And I've got that note written right here, okay? They're never going to be a bracket. We're always going to use the parentheses. And then, just like before, we take our values from that number line, the 6, and yes, the infinity, and we put them inside and separate by a comma. Same thing's going to happen on our next, but now we're going to put a negative infinity here. So when we translate that, the negative infinity will have a parenthesis, comma. We're going to go to the 6, and since that's a closed circle, we use a bracket. Now, one major difference from your past classes is that when you said all real numbers before, you used to use this shorthand notation of a capital R with 2 vertical bars. Instead, all real numbers will now always be represented with this interval notation, and it will look like this. So we're no longer going to use that shorthand notation of that capital R with the 2 vertical bars. Now let's take a look at domain and how we can practice using this and applying this interval notation. In the past, you've only done domain graphically. You've looked at a graph and you have verified and identified what X values were part of that graph. Now we're going to learn how to do this without a graph. You can certainly use graphs to verify your answers, but we want to understand what to do when we don't have a graph. Now, the main idea that we're going to be thinking about in our mind is where expressions are undefined, because values that make an expression or an equation undefined are going to be excluded from the domain. And up until now, you have 2 major areas where expressions are undefined. We'll add more later, but for right now, our 2 main areas are a 0 in the denominator of a fraction and a square root, I'm going to abbreviate, a square root of a negative number. Okay, those are our 2 major ones. And those are the 2 questions then that you're going to use to help you figure out what the domain is. So every problem is going to start off by assuming that the domain is all real numbers, and then we're going to ask if either of these situations apply. So the first one that we'll ask ourselves is, are there, and you're just going to ask these every time, are there any fractions with variables, needs to be a variable in the denominator? If you have, oops, I meant to make that be an n. If you have a fraction with a variable in the denominator, then the domain might have a restriction. If there's not a fraction with a variable in the denominator, you just move on. The second question you'll ask is, are there any even roots? Even roots. Now, typically, our even roots are the square roots that we've been working on up until now, but there might be an even root, such as a 4th index, like a 4th root or a 6th root, and it will look like this one here in part B, okay? It's just going to behave exactly like a square root. Again, if your answer to this is no, then you just move on. So our little summary of that is, if both of these questions are no, then automatically the domain is all real numbers or negative infinity to positive infinity. Because remember, we start by assuming it's this, and if either of these apply, then we look for any restrictions. If neither of these apply, then it stays this. Now, the catch is that it's possible for a problem to have one of these apply, such as this, okay? It's possible to answer yes to one of these questions, and it still have a domain of all real numbers. So an example of that could look like this. I could have y equals the square root, and I could have an x squared plus 1. Now, if you're in my class, we're going to explore this a little bit more when we're in class. If you're not, I would encourage you to type this into desmos.com, and just look at that graph, and you should be able to recognize that its domain is, in fact, all real numbers, even though we have an even root. Now, let's jump into some examples here so you can see how this process is going to work. So the first question that we have here is finding the domain of this question in part A, and the first thing we ask ourselves is there a fraction? Do we have a fraction? Yes. Are there variables in the denominator? Yes. So we're going to focus on the denominator because that is where a domain restriction might happen. So we're going to look at that denominator and we're going to set it equal to 0. So we're kind of mentally setting it equal to 0, but some students even like to write that out. So what we're going to do is we're going to factor that x. Okay, we're going to start solving this. We're going to factor this x, and we'll get an x squared minus a 1, and it's, of course, still equals 0. And then this one, in fact, factors more, and we could keep factoring. And now we can see that we have 3 values that are going to make this denominator equal 0. There are 3 because this exponent in the denominator is a 3. So we're going to put those 3 numbers on our number line, and we're going to put them on there in order. So we're going to have a -1, a 0, and a +1. And since each of those values would make the denominator equal 0, we need to exclude those from the domain of all real numbers, and we're going to visually represent that by putting those open circles there. Now, every other value in this domain of all real numbers is going to give a valid non-zero denominator. So every other value here is acceptable. We could write this problem in interval notation by writing this interval and this interval and this interval and this interval. But another option, particularly on these fraction ones where there's just a fraction, is to use what's called set notation. And what we do is we say x, because domain is the x values, vertical bar stands for such that, and then we identify the things we need to exclude. So we say x not equal to -1, 0, and 1. So our domain is all real numbers as long as x is not equal to -1, 0, and 1. The next one we're going to look at here, we would look at this and we'd again start over with our questions. Do we have any fractions? Nope, we don't. So we get to skip that idea. Then we can move on to, is there an even root? And as we discussed, there is an even root because this index here is an even number. So what we're worried about with even roots is this radicand, this part underneath the radical. We're worried about this becoming negative. Now, 0 is what divides our positive and negative numbers. So what we're going to do again is we're going to set this equal to 0. You can do it mentally, you can do it physically. You could write it down and start solving. Sometimes you're going to need to write it down and actually write it out. So on this one, we're going to set this equal to 0. We're going to start solving. And we'll have 8 equals x squared. We'll take the square root of each side. So we're going to get x equals plus or minus, don't lose that plus or minus, 2 radical 2. And we want to simplify that radical. Now, we're going to put those two numbers on our number line, a -2 radical 2, a positive 2 radical 2. And since at these two values, this expression is 0, and I know that the fourth root of 0 is 0, that is a valid number. It's nothing imaginary. I'm going to make these solid dots because it's still okay. Remember, back here, we made them open because it made a denominator 0. Now what we're going to do is we're going to test these 3 intervals, okay? I do also encourage, until you get comfortable, you might want to fill in those infinities there. Now, when I look at these 3 intervals, okay, if I look at this interval here, this is to the left of a -2 radical 2. Now that might feel like a weird number, but remember, -2 radical 2 is really a negative square root of 8. Well, negative square root of 8, I want to think of what is that close to? Well, it's a little bit less than the square root, negative square root of 9, which means this is a little bit less than 3. So I'm going to test a nice whole number of 3, a -3 here. So if I put -3 into my expression, I get 9 minus, or I'm sorry, I meant to say 8. I got ahead of myself. 8 minus 9. Well, 8 minus 9 is something negative. So this interval here gives me a negative radicand, so I'm going to throw it out. Then I'm going to test here. A nice convenient number is 0. If I take a 0 from here and I put it in my expression, 8 minus 0 is 8. 8 is a positive number, so this interval works. Now we're going to test here. Again, 2 radical 2 is about the square root of 8, so we can test 3, because that's going to be something just a little bit past it. Again, 8 minus 9 is something negative. I cannot have a negative radicand, so I throw this out. That means that my final answer is just this interval right here. And now we're back to what we did up top. The closed circles translate to square brackets. And then we do negative 2 radical 2, comma, 2 radical 2. And that's our domain. Now, we've got one more to do, and this is going to combine our two ideas. First thing we're going to do is we're going to look at our fraction, and we're going to say, hey, we've got a fraction, and we have variables in the denominator. So we're going to start our number line. And the very first thing we want to do is say, where does our denominator equal 0? Because no matter what happens, those values get excluded. And we can see that it's going to become 0 at 3 and at negative 5. So let's put those numbers on our number line. Okay. Remember, put them in order, negative 5, 3. Since they make the denominator 0, we're going to make them open circles and exclude them. We are all done with the question number 1 about the fraction. That's the only thing we care about with that denominator. This problem, we'll note, also has a radical and even root in the numerator. So now we're going to address that concept separately. Just like before, we want to look under the radicand, or under the radical at the radicand, and ask ourselves, where does it become 0? So our radicand becomes 0 at a positive 1. I'm going to put that on the number line. So I'm going to put it here in order. Now remember, at 1, the numerator becomes 0. The denominator is something. Our value doesn't matter, but it's not 0. So 0 divided by some random value in the denominator is allowed, so I can make this a closed circle. Now, I need to test on each side of this 1 because I'm testing this for the radical. So to the left, if I put in, let's say, 0, if I put 0 into that radical, I am going to get a positive radicand, which makes this just fine. Now, technically, we don't have to test over here, but until you get comfortable, you might want to. Let's test negative 6. 1 minus negative 6 is still a positive number there, so it is also just fine as we would expect. If we test over here to the right, if I put a 2 in here, 1 minus 2 is negative, so that radical is going to have a negative radicand, so I throw out that interval. I'm also going to throw out this interval, and we could test it if we want. It would be 4, so 1 minus 4 also is fails. So our final answer is all of this and all of this. And when we write that, what we're going to do is fill in that negative infinity. So we'll say parentheses, remember always with the infinities, negative infinity to a negative 5. This open circle is going to become a parenthesis. Now, sometimes we have multiple intervals like we do here. I need to join this group with this group. So I'm going to put this U here. It stands for union and pulls it together. And now I'm going to write this interval. So I'm going to have, again, that parentheses for the negative 5. And I'm going to go up to a 1. And I want to use a square bracket there. Now, this is a lot of information that we've thrown into this. So once you're done, maybe jot down some questions, some parts that you thought were confusing, and then we are going to practice this a whole bunch more in class.